Hi, welcome to ESI 521 Pattern Generation at the Nanoscale. I'm Professor Ukjun Nam at the Pennsylvania State University. We're going to talk about scanning probe microscopy lithography. This is another way um, of transferring the patterns using the direct writing. So here is the outline. I will give you some overview in scanning probe microscopy because this technology is based on this scanning probe microscopy technology. And then we will move to deep-pen lithography. And then we will talk about ensom lithography. And then finally, we will talk about the scanning tunneling microscopy, atomic manipulation. Actually, for this technology, instead of I used lithography, I called this technology as an manipulation because the way of is transferring the pattern is kind of a little bit different from traditional way of the lithography. So we will talk about that more in details during the later of this lecture. So scanning probe microscopy, it has very many kind of techniques are available. So one is an atomic force microscopy, and then scanning tunneling microscopy, and then near field scanning optical microscopy, and then magnetic force microscopy, and there are lots of kind of a variant based on the signals these kind of techniques are using. But all these kind of techniques use cantilever, and then there is some kind of feedback systems, and then also use some lasers and a photodetector. So based on that kind of a basic configuration, I will show you in the next slide. They are all under the umbrellas, big umbrellas of the scanning probe microscopy. So this scanning probe microscopy is normally used for the analysis of the material characteristics. So some of the technologies like an STM or AFM offers atomic resolution of the images of a surface of a sample. So it is kind of one of the most popular way to analyze the topography or morphology of a surface of a sample. And then some other techniques also offers different kind of material characteristics. And then some also provide some other kind of a spectroscopy analysis using Raman spectroscopy. So each of these kind of different kind of technologies can be used for different kind of material characteristics. But these kind of techniques also can be used for the pattern transfer. So those kind of way of using these kind of technologies for making those kind of pattern transfer we're going to talk about today. And as to the signals, the atomic force microscopy using the signals, actually the atomic force between the cantilever tips and then the surface of the sample. So if there is two atoms present, depends on the distance between two atoms, it has this kind of a relationship. So this is a force and then this is a distance. So as this distance of two atoms getting closer, it just attract each other. And at some point, if this kind of distance are getting too close, these kind of two atoms started to using a repulsive force each other. So it just started to push each other. So its forces just changes like this. So depends on the distance and then the force between the two atoms. The AFM is just using three mode. One is a contact mode or non-contact mode or a tapping mode. So all these kind of three modes are based on distance versus the atomic force between these cantilever tips and then the sample surface. As to the scanning tunneling microscope, both of the cantilever tip and then samples, both of them are conductive. So we flow a current from the tip to the sample, and then because we have a space between the tip and the sample surface, those kind of electrons should jump to the tunneling through the sample surface to conduct the current. So that is why we say it is a tunneling microscopy. And for this technology, people using an electrical current. And then near field scanning, optical microscopy, as the name of the technique implies, it uses light. So this is the configuration, typical configuration of the SPM. For this specific example is an atomic force microscopy, and then especially for the tapping mode. So as I just mentioned briefly, so it has an cantilever, and then there is a laser. So the laser just hitting the backside of the cantilever and then bounce back to the photodetector. So this photodetector is connected with a feedback loop. So depends on the signal changes, this kind of a feedback loop just controlled these piezo stages. So using that way, we can scan three-dimensionally X and Y and Z directions, and then we can also adjust the distance between the samples and then cantilever. So this movie will tell a little bit more about the details about how this kind of SPM works.
Scanning probe microscopy refers to a group of imaging techniques that collect tapping mode is used to. Scanning probe microscopy refers to a group of imaging techniques that collect images of a sample surface by moving a probe over that surface in a raster pattern. As the sample moves, the probe records the height of the surface. Scanning tunneling microscopy was the first scanning probe technique developed by Binning and Royer in 1982. Atomic force microscopy is the most commonly used scanning probe technique. Tapping mode microscopy, magnetic force microscopy, electric force microscopy, frictional force microscopy, and near-field optical microscopy are a few examples of a long list of scanning probe techniques in use today. All scanning probe techniques have a small probe, a feedback method, and fine control of the distance between the tip and the sample surface. Various methods are used to send a signal to the feedback. The feedback control assesses the distance between the tip and the sample. If the distance is too small, the feedback loop signals a piezo crystal mounted at the base of the sample to contract, lowering the sample. If the distance is too large, the feedback loop signals the piezo crystal to expand, raising the sample. An image of the sample is created by plotting its horizontal and vertical movements as the tip scans across its surface. An image of the feedback signal is also produced. This indicates how well the feedback loop is controlling the tip-sample interaction.
So as we continue this kind of sample scanning, X and Y, and then the stage also moved to the Z direction. So as we just raster the samples, we can make the final images something like this shown in the picture. So if we want to analyze the topography information, we can just selectively choose one dimension, and then if we just draw a line, and then we can just see the topography information of that specific area. And then since we are talking about scanning tunneling or microscopy, and then deep pan lithography, which is based on the AFM technology, so we will continue to hear about how those kind of two techniques are working.
A scanning tunneling microscope consists of a conductive metal tip positioned approximately 10 angstroms from a conductive surface. An electrical potential of 10 to 40 millivolts is placed between the tip and the sample. This creates a conductor, insulator, conductor structure with an insulator thickness of 10 angstroms. Quantum mechanics predicts that a small number of electrons will tunnel through a short barrier. The number of electrons, or the tunneling current, is related to the barrier thickness. When the barrier thickness is less than 10 angstroms, the number of tunneling electrons increases, strengthening the tunneling current. When the barrier thickness is greater than 10 angstroms, the number of tunneling electrons decreases, weakening the tunneling current. A constant current STM image is created by scanning the STM tip over the surface, while keeping the tunneling current, and therefore the tip sample distance, constant. The tunneling current is monitored by a feedback loop. The feedback keeps the tunneling current constant by raising and lowering the sample stage, which in turn keeps the distance between the tip and the sample constant at 10 angstroms. The topography image is a plot of the movement of the sample up and down under the tip, while the current image results from plotting the actual tunneling current. Atomic force microscopy uses a silicon nitride tip mounted on the end of a silicon cantilever spring. Feedback is based on a change in force between the tip and the sample, which changes the angle of the cantilever and moves the spring. A laser reflecting off of the back of the tip moves up and down on a detour as the spring moves. The feedback loop reacts to a change in laser position by adjusting the height of the sample in order to keep the force constant. The topography image is created from the path of the sample moving up and down, while the deflection image is based on the deflection of the tip. The AFM operator adjusts the feedback controls to minimize the deflection of the tip, increasing the accuracy of the topographic image.
So this specific technique of the AFM technology, this video showed you was an contact mode. So that contact mode of the AFM just monitoring the deflection of the cantilever upon it is kind of scanning the surface of the sample. As I mentioned in the previous slide, there are two other modes, and then the last cartoon will show you another kind of a mode of the AFM, which called as a tapping mode.
Tapping mode is used to image soft samples that could be damaged by the nanonewtons of force that are present in atomic force microscopy. As the name implies, the tip oscillates as the sample is scanned. The amplitude of the oscillation is used as the feedback signal. Tapping mode is used to image soft samples that could be damaged by the nanonewtons of force that are present in atomic force microscopy. As the name implies, the tip oscillates as the sample is scanned. The amplitude of the oscillation is used as the feedback signal. Tapping mode is used to...
So, as I just mentioned, basically each of the different kind of technologies just use a basic configuration, which is like a cantilever, and then the laser, and then photodetector, and then a feedback loop, and then the signal is kind of different based on the monitoring signal is different based on the technology. So this is the one of the example of the morphology analysis, which is a platinum film using the scanning tunneling microscopy. So as you can see, all these kind of circles represent one platinum atom. So since it offers kind of a very high resolution atomic images, even we can observe this kind of defect, point defect on that surface. So because of this kind of a very good and precise high resolution images, these techniques are used for that kind of a material characterization. But today's kind of scope is kind of a little bit different since we're gonna use this one as an pattern transferring technology. So let's talk about deep pen lithography. This one is basically using atomic force microscopy. So the basic is very similar. Basic operation of the deep pen lithography is very similar to using this kind of a fountain pen. So we have a very sharp tips in the pen, and then it also has this kind of an ink. So this is the typical configuration of the deep pen lithography. So this is the pyramid structure of the tip, and then it is kind of connected with this kind of a cantilever bar, and then the laser might hit something like this. And then interesting thing is this is an ink material, and this ink normally has this kind of a material we wanted to deposit directly. So in this example, this ink containing this kind of polymers. One end is an thio, and then polymers, and then this substrate is on gold. So these thio molecules just to bind with the gold, just assemble to the gold. So as these tips moving toward this direction, this kind of polymer bar structures can formed directly. So this is a little bit different from the traditional lithography technique, because in the traditional lithography, as we talked about the e-beam lithography or optical lithography, in that case of that, we spin coat some material which is an photosensitive material for the optical lithography, and then we just expose some areas, and then just remove that area, exposed area, or remaining the exposed area, depends on the type of the resist. And then during the following processes, we make this kind of a final material deposition or removal. But in the deep pen lithography, it just skip this kind of an exposure and then development process, but it just directly forming the target materials with whatever structures we want to achieve. So in a sense, some people just classify this kind of a deep pen lithography as an additive manufacturing, or this is another kind of techniques as an bottom-up approach. So this deep pen lithography, or this kind of SPM lithography, scanning probe microscopy lithography, sometimes classified as this kind of bottom-up approaches or additive manufacturing, because we directly build this kind of target materials with whatever structures we want to do it directly. So to help you understand, I will show you another kind of a video. So this is the videos showing how those kind of deep pen lithography is working. So as you can see from this point, the structure of the tool is almost similar to the AFM. So you can see the AFM tips are just mounted over here, And then if we just to take a look at much closer, those kind of a tip end is kind of wet by the ink material. So as we just make the distance between the tips and then the substrate closure, this ink material started to wet the surface. And then we can just draw the pattern as we want. But as you may expect it, if we are using one single tip, those kind of throughput might be very slow. So to improve those kind of throughput, as we discussed in the electron beam lithography, instead of using multi-beams for the electron beam lithography, people can use multi-probe stages at the depend lithography. So instead of one single probe, these cartoons use 1, 2, 3, 4, 5, 6, 7, 8 probes at the same time. So in this case of that, those kind of writing time is much faster. So using that way, people can increase the writing time. And then this is the actual result written on an actual paper. So the size of the letter is 65 nanometer wide. So this is an actual written result. So this is another kind of an example of the written result. So basically it is easy to write down the pattern size smaller than 100 nanometer. And then if people want to go down to 50 nanometer, it needs some careful calibration. And then so far about 10 to 15 nanometer feature size of the patterns were demonstrated using this DPN lithography, or in another word, DPN lithography technology. So let's talk about near field scanning optical microscopy. So this ENSOM application is basically this ENSOM technology also used for material characterization, especially it is kind of originally developed for the optical imaging. But using the spectroscopy connected with the spectroscopy like an Raman spectroscopy, it can also analyze the material, and then depends on what we connect to that probe. We can also use this one for lithography, which we will talk about today, and then it can also be used for the other kind of one application as well. So unlike AFM or STM, which is using an atomic force or electrical current, ENSOM uses a light. So when we use just an optical microscopy, its resolution is around 250 nanometer, because when we apply the way of we are applying the light for the optical microscopy, it has a lot of kind of a light diffraction limit. But if we are using a very small cantilever, kind of which distance is kind of very close to the surface, we can just minimize this kind of a light diffraction issue. So we can just technically achieve reduce the resolution to the 50 nanometer, and then so far 25 nanometer of the resolution has been demonstrated using an 488 nanometer of the laser source. So basically using this kind of ENSOM, people can achieve much better resolution of the optical images. And then this is the typical configuration of the ensom. So this tip is transparent, and then there is an this kind of a tuning fork, and this tuning fork just to make fine tunings of the distance between the tip and then the surface of the samples. And then if this is used for an optical imaging, there are lenses and cameras positions underneath of these samples. So you can just do the optical imagings using that way. But for this particular application we will discuss today, we will use this one for the lithography. So this configuration may not need it for transferring those kind of patterns. So this ensom has two different type of the tip. So the core of the tip is made out of the transparent materials like glass. And then the outside of the transparent tip is coated by metal. In another word, we call this metal layer as an aperture. So one type of the tip is kind of coated by this kind of metals, and then another type of the tip does not have any coatings, and then it just simply has an transparent tips. So there is a trade-off between these aperture or apertureless tips. Actually, the aperture tip has a very dull tips, but this apertureless tips has a very sharp point. So it just has an it will provide a little bit better resolution. But the thing is, without aperture structures, just making much more complicated feedback processes. So in the final images, this type of the tip is much easier to use. So this type of the tip is much more preferred method. So when we use this ensom for the lithography, this is very similar to the traditional way. So on substrate, we will coat photoresist, which is a photosensitive material. And then using this one is a case of the apertured tip. So we can just simply apply the UV light through the this kind of tips. So we have a very small kind of a spot on the photoresist. So it just minimize those kind of diffraction issues. When we use an apertureless tips, which is two different type. One is an just a transparent tip or metal tip. Both of them are apertureless. So in this case of that, we can apply the light through the tip. But in this case of that, since we don't have an aperture, it is kind of very hard to control this kind of another the light coming outside of the not only from the tip, it also coming out from the other side. Even though in terms of the intensity of the light, it is highest in intensity at the tip, but it also has some intensity from the other side of the exposure. So it's kind of a little bit complicated than this type, aperture type. And then when we use a metal tip and we apply the light from the outside at the very sharp point, it has a much higher intensity. So using that way, we can also use this kind of a mechanism to expose certain areas. But this type of the exposure of this kind of photosensitive material is also very complicated compared to this approach A. So approach A is a much straightforward way to expose this kind of photoresist material. And then as we raster to transferring the patterns using electron beam lithography or ion beam lithography, we can move around these tips. And then as I showed you in the previous cartoon, we can just draw whatever patterns as the depend lithography can offer. And then this is an example of the anthem lithography. So you are looking at the very tip of the cantilever. So this is the, if cantilever looks like this, if then you are seeing the hole at the very tip, and then it looks like a bow tie like structure. So for this specific example, people apply the focused laser beam through the cantilever beam, and then those kind of a laser beam just pass through this bow tie like pores, and then it can just expose that photosensitive materials coated on substrate. So people just draw this kind of a circular shape. So using this kind of a way, this specific example can achieve 24 nanometer width of the line patterns. Another one is this is the combination of the anthem and then depend. So this tip looks like an the depend cantilever, but it can just have multiple tips mounted together, and basically the polymer layer is kind of transparent, and then the gold coating works as an aperture. So it is kind of very similar to this anthem lithography is doing, and using this kind of photosensitive materials, so we can just directly writing whatever patterns we want to write. But in this case of that, it has a multiple probes, array of the probes, so its writing time is much faster. And then in this example, the dot size is on about 111 nanometer dot size. So the last example of this scanning probe microscopy lithography, we will talk about the scanning tunneling microscopy atomic manipulation. So this is a typical configuration of scanning tunneling microscopy. So it has a piezo electric tube. Depends on the system, this kind of piezoelectric tube can be positioning under the substrate stages, but in this specific example, it is positioned on the side of the tip. So as I showed you in the previous cartoon, it's just monitoring is kind of a tunneling current. So using this kind of a tunneling current, you can just make this kind of images, but for atomic manipulation, using this kind of a current, we can move around this kind of individual atom. So this STM technology is normally operated in a high vacuum environment, so that is why it is kind of much more controllable, and then the feedback signals as I showed you in the previous cartoon. So this is one of the example people's manipulating this each of the individual atom, and then people created a movie based on the individual atom manipulation. So I'll show you these videos as an example. each of the dot you are seeing in this cartoon represent each of the atom. So in the next video, I will show you how people can manipulate this kind of an individual atom using this kind of an STM technology.
In a significant move forward in the march toward creating electronic circuits that are thousands of times smaller than today's most advanced technology, IBM is announcing a milestone in the ability to manipulate and understand matter at the atomic level. Scientists at IBM's Almaden Research Center in San Jose, California have for the first time demonstrated the ability to measure exactly how much force is needed to move individual atoms. Knowing the different forces required to move different atoms will allow IBM's nano-constructionists to figure out which materials should be used for building devices from the atom up. For example, a so-called sticky atom would be used for something that you don't want to move, like a base that you want to keep in one place, while a so-called slippery atom would be used when you want to build something like an on-off switch that needs to move with ease.
10 or 20 years ago, nobody could imagine that we would have today laptops, cell phones, and iPods. I think it's impossible to speculate what nanoelectronics will bring us in 10 or 20 years, but I'm sure it will change our world even more than the iPods we have today.
The force is measured via tiny changes in the frequency of a small quartz tuning fork. This exploration of the realm of atomic-scale structures and devices stands to impact the future direction of information technology. This is Jeff Gluck reporting.
So this video showed how we can manipulating this kind of different kind of individual atoms, and then based on the different materials used for this kind of manipulation, and then the background materials, we can just controllably manipulate each of the individual atoms. So using this kind of technology, we also can apply this kind of technology for a practical application, not only for creating a movie that I showed you. So next slide, I will show you one more example where we can potentially use this kind of technology for a practical application.
At IBM, we are interested to understand how the magnetic properties evolve from the individual atom to something that might be useful for a technology for data storage. We as an industry have been following for many years this trend that we now call Moore's Law, where we exponentially shrink the components down by a small factor every year. Now what we are allowed to do in this laboratory here is we're allowed to jump to the ultimate end and start with single atoms and build structures one atom at a time. In this breakthrough, what we have done is we have stored magnetic information in only 12 atoms. We have this specialized tool that allows us to investigate the properties of single atoms and small clusters of these atoms. And now for the first time, we've actually seen that these 12 atoms behave like a stable magnetic unit. So a current computer hard drive, for example, stores information in a large number of magnetic atoms. And all these magnetic atoms act together to make one bit of magnetic information. And so if we can scale down, then we correspondingly get a much larger density or much larger number of bits in our disk drive or in our computer. Here you see a representation of a single magnetic bit consisting of 12 atoms that we built with a scanning tunneling microscope on this surface. The tip of the scanning tunneling microscope can also be used to switch the magnetic information on this bit from a 0 to a 1 or from a 1 to a 0. Now we're zooming out from the single bit to 8 bits, which makes 1 byte, which is the next bigger unit of information in a computer. A byte, for example, can store all the characters that you have in the alphabet and all the numbers that go with it. If we zoom out further, then you can see that we can put many of these bytes next to each other. In this example here, we have 5 of those, and they store different information in them. In this case, the letters T, H, I, and K. In this size comparison to existing technology, you can appreciate how much smaller this atomic scale magnetic data storage could be and how much more information you could store in the same space on your drive.
So this is a little bit different, just compared with those kind of lithography technologies we have discussed so far. But it is kind of a pretty interesting technology. It just allows us to manipulate each of the individual kind of atom manipulation, and then it's kind of a very small in scale. And then those kind of depend lithography, as you may remember, those materials are transferred in liquid form. So this kind of a technology also very suitable for those kind of biological device fabrication. So instead of we are just drawing some patterns using those kind of ink material, we can just apply different kind of different sequence of the DNAs or different proteins in each of the different kind of wells. So we can just easily make biosensors or chips using this kind of depend lithography. So the reason why we call this all variation of the variant of the scanning probe microscopy lithography as a direct writing is like the other kind of a direct writing method, like an E-beam lithography technology or ion beam lithography technology. It does not need a physical mask to transfer those kind of patterns. It only needs an electronic version of the design. So in a sense, once we have those kind of a design, we can just directly write whatever that designs directly onto the substrate. So in a sense, this technology is also classified as a direct writing techniques. In addition, this direct technique also suffering those kind of a big drawback as an throughput. And then as we kind of used those kind of multiple beam for this kind of SPM lithography, also can use those kind of multiple probe. So using that way, we can increase the throughput of this kind of a technology as well. So this is the last lecture for Unit 2, which we discussed about direct writing. So from the next lecture, we're gonna talk about nano imprinting lithography. Then see you next time.